Okay, guys, just wanted to take us through the 12 basic functions as our next section that we're looking at here in this first chapter. Like I said in class today, the first section we talked a lot about the ways we can describe functions, whether they're increasing, decreasing, bounded, whether they have maxes and mins, what their domain and ranges are, all those things. But now we're actually going to look at some different functions, but we can use our vocab that we picked up last section and we're just tested on as we describe these things. So quickly, these first few are really, really fundamental. This first one, the linear function y equals x, couldn't be, as I said, a more basic of all basic functions. But note the domain and range. All real numbers go in, and of course, because the y value is literally the x value, all real numbers are going to come out. So when x is 7, y is 7. When x is 2, y is 2. When x is negative root 3, y is negative root 3. End of behavior, obviously we are heading up as we move to the right and down as we move to the left, so you should be able to do something like this. As we move to the left on the x-axis, our y values are moving down, going to negative infinity, and as we move to the right, our y values are going up. Now, I'm not going to take the time to write out the end behavior for every one of these functions, but it's something you should be thinking about and should be able to do on your own. Next example, the quadratic function. Anything that has the 2 as its highest power, as its degree of that function, is going to be a quadratic function. X squared plus 3x plus 5. I'm just showing you here what the most basic quadratic looks like with its vertex, its absolute min at the point 0, 0. So you can see the domain again is all real numbers. There are no numbers that you're not allowed to square. Any number you can take and multiply by itself. But when you do that, you're guaranteed to get a non-negative number. So there's maybe one of those phrases that we're going to talk about, non-negative. You might say, well, why didn't he just say positive? That's going to be 0 plus the positive numbers, okay? And then, of course, we can talk about non-positive, which is, of course, 0 and the negative numbers. All right, so that's kind of a fancy mathematician way to say 0 plus negatives is non-positive. Anyway, we have a non-negative range here. X can be 0, y can be 0, but everything will be positive after that. So then we go to the cubic function. And the cubic function doesn't look a whole lot different than the linear function, except it's got a curve to it. Again, I think I mentioned in class that if I were to come up with my own list of 12 basic functions, I probably would not include x cubed because it's just not very different from x. I mean, sure, it has a curve to it and it's going to increase more quickly than y equals x, but we're going to find later on that x to the 5th and x to the 7th and x to the 9th and so forth, all of these functions are just exaggerated versions of x and x cubed. Domain is all reals, range is all real. There's not a whole lot of stuff going on with these guys. I did want to maybe go back to this quadratic function and just say that this is a function that is bounded below because there is an x value, there is a y value that is less than or equal to all y values that this function achieves. So it's bounded below at y equals 0. Of course, linear and cubic are not bounded below or bounded above or bounded because they go up forever and down forever. So now we move on to our fourth one. This is kind of where we finished up in class today, but we talked about the square root function and we looked at the domain, which does include 0. The hard bracket includes 0 because you can take the square root of 0. It is simply 0. So your y values start at 0. This function moves up as you move to the right and will continue to move up as you move to the right. It's not going to be linear like that, but it's going to continue to go up slowly, but it's going to continue to rise. So this function, again, would be bounded below. It's a function that's strictly increasing. As we move to the right, our y values go up. So there's a few more phrases we could use to describe this thing. And I think that'll be good for now. Now, these next couple, the next three, example 5, 6, and 7, are going to involve some concepts that we haven't really talked about yet. So I think with this video I can take a little bit of time without using class time to show you what's happening with the natural logarithm function. We'll talk a little bit about logarithms, although we're going to study them in detail in Chapter 3. And the exponential function, which involves this number e, which is one of the most powerful and prevalent numbers in all of mathematics. And then this logistic function down here, which again involves e, okay? So I think the first thing to do is talk about what e, this number, is. And I think I'm just going to explore it for you this way. If you consider the number 1 and 1/10, but if you were to raise it to the 10th power. So that would be 1.1 to the 10th power. Now, I'm sure you don't know what that number is off the top of your head, but you would say, okay, well, it's a number that's pretty close to 1 being multiplied by itself 10 times. So it's going to get bigger than 1, but it's not going to get huge because, multiplying 1 by itself 10 times is going to just be flat line stuck at 1. But 1 to the 10th, 1.1, 1 and 1/10 raised up to the 10th power, actually turns out to be about 2.594. And I'll put a approximately equal to, because of course I've just stopped at the thousandth. Now, what if we took a number that's even closer to 1, like 1 and 1/100th, but we raised it to the 100th power? So now we're taking the number 1.01 and multiplying it by itself 100 times, okay? So that's going to be a whole lot of multiplications. For example, take a number like 2 and raise it to the 30th power. For example, 2 to the 30th is, we are up in the 100 million range, 107 million. That's huge, okay? Because this thing keeps doubling, all right? So what's going to happen when this number, is multiplied by 100 times of multiplications, but yet the number itself is very close to 1? So it begs the question, is this thing going to blow up and become something in the, tens, thousands, hundreds, millions, or is it going to be somewhat like close to 1? So if we try it on our calculator, we take 1.01 and raise it up to the 100th power, we actually get a number that's not terribly different than what we got with 1.1 to the 10th power. We get approximately 2.705. Okay, so it was a little bit bigger than our first guy, but not a ton. So that's like, okay, well, what's going to happen if we did 1 and 1/1000th and raised it to the 1000th power? So I'm going to put it again, approximately equal to, and we'll go to our calculator, and we're taking 1.001 and raising it to the 1000th power, and we get 2.7169. 2.7169. I've gone out to the 4th decimal place because we didn't change a whole lot from where we were. So it seems as though this expression, as I do 1 plus 1 over x, but I raise it up to the xth power, and we're looking at what's happening with these y values that we were getting when we were doing that. As x gets larger and larger, it begs the question, what's happening with this thing? And we saw when x was 10, we were at, say 2.6. And when x was way out there at 1,000, we had only changed a slight amount. We were at, 2.7. So this thing appears to be kind of like leveling off, maybe at some horizontal asymptote. Well, the question is, what is that horizontal asymptote? And you can try it on your own. You can do 1 plus 1/1,000,000th up to the 1,000,000th power. Or 1 and 1/1000,000th up to the 1,000,000th power. And your calculator will do it. You might want to count your decimals carefully. But what's going to happen is you're going to find that your y values basically will be more and more alike, and you'll have to go 6, 7, 8, 9 decimal places out before you find any change. If you went, say, between 1 and 1/1,000,000th and compare up to the 1,000,000th power and compared that to 1 and 1/1000,000th up to the 1,000,000th power. What happens is this horizontal asymptote is a particular number, 2.718281828, and it's not a repeating decimal, I think that's actually an approximation. This is not a number I have memorized out to 50 places or anything like that. But it is an irrational number that has obviously no repeating pattern, cannot be expressed as a ratio of two integers. If you think about what other irrational numbers have you come across in your life, probably the most famous one that you're aware of is pi, which again is a non-repeating, never-ending decimal. This number is so powerful that it gets the name E, and it's named for a guy named Leonhard Euler. I think he was Swiss, so I think the spelling of his name Leonhard is something weird. Like I think he's got an H in there, and the last name is Euler. And in German, that EU sound is kind of like oi, like Euler. You might hear Euler, but I always say Euler. Anyway, this number was given the letter E, named after him. He was a Swiss mathematician, like I said, that had done a ton of work in all sorts of different fields of math. But this number E is right up there with pi and maybe the golden ratio, phi, as being three of the biggest, most important numbers in mathematics. And we'll explore how this works when we get to chapter 3, and how this number E comes up as what's called a natural base. So when we have exponential equations like 2 to the x or 5 to the x, those are called exponential equations because the exponent is a variable. Well, E shows up in exponential relationships, so it's referred to as the natural base. So the kind of fundamental exponential equation is written as y equals e to the x, or f of x equals e to the x. And so we see that here in example 6. There's our basic kind of nuts and bolts exponential function. And it looks like Mr. Kegelman has a big typo on his sheet because I forgot to change this graph. You may have noticed that this graph is the same as that. That's because I copied and pasted without changing it. So I'm glad we looked at this. The actual exponential function looks like this. It starts real small and goes up and gets real big. Now, I'm going to come back and talk about the natural log function in a little bit. But let's get rid of this. This is what the natural log function looks like. So e to the x has been shown here right there. And if you think of this number 2.718 and why its graph would look like that, if we took 2.718, let's just get a couple of data points here. Let's take it to the 0th power. So when x is 0, your y value, of course, is 1. So you're going to have, I didn't draw that very accurately, but you would have the point 0, 1. So it's going to come through there and hit 0, 1. Now, when x is 1, you'd get 2.718 to the first power, which of course is 2.718. So you'd be over here at 2.718, so it's going up there. And then you can see as our x values increase, I don't know, 2.7 squared is going to be something like, I don't know, 6 or 7 or so. We could just, let's say it's about 7. So it's going to go up here, and it's going to continue to rise really quickly. Now, when you go to the negative side, 2.718 to the negative first, so when x is negative 1, you're going to get 1 over 2.718. Well, that's going to be approximately 1/3, which is approximately 0.3. So as you go to negative 1, you're going to have these small y values that are down here close to the x-axis. And by the time you get to 2.718, let's say to the negative 10th, you get 1 over 2.718 to the 10th. Well, that's going to be a really big number, but it's in the denominator, which is going to make your fraction really small. So the closer we go out here to the left, the closer you're going to get toward y equals 0. But you're never going to hit 0, because I don't care what x is. Let's say x is negative 1,000. 2.718 to the negative 1,000th power is 1 over 2.718 to the 1,000th power. Now, that is a really big number, but your numerator is not 0. Your numerator is 1. So I don't care if this turns out to be 37 cajillion. You have 1 37 cajillionth. So it's not 0. So there's the typical exponential function. You may have explored that like 2 to the x in your Algebra 1 class. A lot of textbooks do that. But that guy is right there. And again, I apologize for that graph that I put in there. That's actually the incorrect graph. So now we can kind of go back to example 5, which is a logarithmic function. And this guy has to do with answering a question about what an exponent would be. So if we have the phrase, for example, log base 2 of 8, and this is called a logarithmic expression. The question that this expression is asking, log base 2 of 8, is saying what power is required to take this number and turn it into that number. So you're really answering the question, 2 to some power equals 8. And of course, we all know just by our life experiences that that answer is 3. So these functions are kind of the inverse, and we'll talk about inverses in the next section, of the exponential function, because the exponential function gives you the exponent, or you plug the exponent in and it spits out an answer. Like when the exponent is 0, the answer is 1. When the exponent is 1, the answer is e. When the exponent is 2, the answer is 7-ish. When the exponent is -1, you get an answer. So you plug the exponent in and it gives you a number out. A logarithmic function, y equals log base 2 of x, when you have that, what we're sort of saying is your input is sort of going to be the answer of an exponential equation. So it's going to look like this. What exponent do you have to plug into? To turn this base into this number? Okay. And what happens there is you get a curve that looks like this, and it goes out and it grows, but really slowly. You could imagine something like log base 2 of 32, okay, and the y value on that. So this is saying what power do we need to use to raise 2 and make it turn into a 32? Well, most of you probably know that 2 to the 5th is 32. So in log base 2, you would have to go all the way out to an x value of 32 before you had a y value of 5. And you could imagine if we did log base 2 of 64, that answer is 6. So you'd have to go all the way out to 64 before you move up one more unit and get a y value of 6. So this thing is going to grow very slowly. The wrap on logarithmic functions is that they are the slowest increasing functions. So now, domain and range on these guys. Back to example 6, the exponential. I probably should have made that example 5. The exponential function, you can put any number you want in there. You can use any number you want as an exponent. But what you'll see is the range values, even when I put a -1,000 in there for the exponent, the y value was never going to go to 0, nor was it ever going to go negative. So those range values are 0 to infinity. Now, when you jump up to example 5, you might say, well, why can't you have 0 or a negative argument? Argument is what we refer to as the thing inside the parentheses there. So if we tried to do something like log base 2 of -8, that's asking the question 2 raised up to what power gives you -8? Well, we just talked about this. There's no power in the world that you can raise a number to turn it negative, okay? We saw that down here. These functions in the exponentials never went negative. So for that reason, this thing can't be negative. Likewise, to say log base 2 of 0, that's equivalent to saying 2 raised to what power is 0? You might say, well, the 0 power. No. 2 to the 0 is 1. 2 to the 0 power is 1. There's nothing we can do to kill all these factors of 2 to turn it into a 0. So that's why your domain there is 0 to infinity. And again, we're going to do an in-depth study of exponentials and logarithmic functions later on. For now, it's just enough to recognize what their graphs look like. So as long as you corrected this graph down here, the exponential function, to kind of look like that, it is a increasing function the whole way, as is the logarithmic function. As you move to the right, the y values go up. But that's all you need for now. Know that they're increasing and know what the domains and the ranges are. And I'll just ask this probing question. Maybe I'll ask you guys again tomorrow after you've thought about it. Did you notice anything about the domains and ranges of 5 and 6? Anything, any pattern or anything like that? Now, moving on to example 7, the logistic function. Very funky looking little graph here that we have two different horizontal asymptotes. On the left, it's heading off toward y equals 0, and on the right, it's heading off toward y equals 1. And it's kind of curious. It's like, what kind of what would you have to be going on in this mathematics to make that work? I will show you maybe a slightly different version of the logistic function. This is the basic one that's shown here, the kind of fundamental one. But let's use, instead of e, let's use the number like 3 as our base. So if we had 1 plus 3 to the negative x power, and let's just use maybe 3 data points. Let's use x equals 0, and like x equals 10, and x equals negative 10, just to kind of see what would happen with this thing. So with x equals 0, we'd have 1 over 1 plus 3 to the 0, which is 1 over 1 plus 1, which is 1/2. So there you go. When x is 0, we have a y value of 1/2. When x is 10, though, we'd have 1 over 1 plus 3 to the negative 10th, which is 1 over 1 plus 1 over 3 to the 10th. Now, I don't know what 3 to the 10th is, but I know it's a really big number, and I know 1 over 3 to the 10th is basically 0. So this is like similar to 1 over 1 plus 0, which is basically, oh, sugar pops. I just realized I didn't mean to have a negative there. That should be e to the x instead of e to the minus x. So let's make that guy a positive. And you can see what's going to happen when this guy is positive. Hold on. I'm sorry. Yeah. Okay, sorry about that. I just went back and kind of erased some of my work there and made it a little bit more clear what's happening here as you get large values of x. And again, this is okay, what we have here, which is 1 over 1 plus e to the negative x. I started to have a second guessing myself because I wrote this note sheet in a little bit of a hurry last night. Anyway, so at x equals 0, you can see that over here, we put 0 in. I used a base of 3 rather than e just because it gives us, it's a little quicker to compute things. But 1 over the quantity 1 plus 3 to the 0 is 1 over 1 plus 1, which is 1 over 2. So we got that point right there. Now, when we toss in a 10 here, because of that negative exponent there, we have to take 1 over 1 plus 3 to the opposite of 10. Now, again, 3 to the negative 10 is going to be virtually 0. It's not exactly 0, but it's 1 over 3 to the 10th power. So we're going to be really close to a y value of 1 over 1. Which, as we got really close, as x went out to 10 here, we got close to a y value of 1. It's not going to be exactly 1 because there's a little bit of stuff here that makes the denominator a little bit bigger than the numerator, which gets us close to 1. But now, when we go to the other side of the x-axis and we plug in negative 10, so we have 1 over 1 plus 3 to the opposite of negative 10. So that's going to turn into 1 over the quantity 1 plus 3 to the 10th. Now, what's going to happen to this denominator is it's going to get huge. So you're going to have something like 1 over a really big number, okay? And 1 divided by a really big number is going to get very close to 0. So that's what's happening on the left side of the graph. So again, I apologize for that work there. I kind of froze up, paused it, went back and erased it just to make it look a little bit clearer. But there you go. So that's a really interesting function that kind of starts close to 0 and then comes up and then maxes out at 1. And what we would experiment with would be what would happen if we had something where the numerator wasn't just a 1. What if it was like a 300 there? Over 1 plus 3 to the opposite of x. And what's going to happen is on the right side now, when this quantity here for large values of x, you'd have like 100. Well, 3 to the negative 100 power would be basically close to 0. So you'd be taking 300 and dividing it basically by 1, which would get you about 300. So that numerator there is going to change the right side of this graph. Rather than level off at 1, now it would level off at 300. And so for that reason, that numerator is called the limit to growth, because our function can never get bigger than that, because we're always going to be dividing by 1 and a little bit, okay? Taking 300 and dividing it by 1.000001 is just going to be a number that's like 299.99999, really close to 300. So it's never going to get above 300. But then again, on the other side, when you put in large negative values and take their opposites, you're going to have 1 plus 3 to a giant power. Like if you put in x equals negative 100, you're going to get 3 to the opposite of negative 100, which is 3 to the 100th power, which is really, really big. And you're going to get 300 over a giant, giant number. And I don't care. You put 300 over a really big number, you are going to get basically 0. And that's why the graph levels off at 0 on the left. And there are a couple of not fun, but like very, very applicable to real-world situations uses for logistic functions. Okay, that last slide was a doozy. It was like a 20-minute slide because there was a lot of background we had to go and fill in there before we knew what those functions would look like. But in this one, we're back to some maybe somewhat familiar stuff. We've got our classic rational function. Remember we talked before our last test about rational functions where you have a function being divided by a function. So we could think of y equals 1 being a function and y equals x being a function, and the ratio of those two functions is another function. So you're going to get domain issues here. And we know very well that we're not allowed to divide by 0, and so therefore you see that domain of avoiding 0. So everything from negative infinity up to 0, don't include 0, skip over, and then pick up everything to the right of 0. So you can see the graph has a red wall of death in there, a vertical asymptote at x equals 0. Because we get no y value, because we have no x value at 0, we're not going to have a y value when x is 0. So that's why we show up with a vertical asymptote. Now, as far as what the graph looks like, you can think about, if you put in x equals 1, you get 1 over 1. So when you come over here to x equals 1, you get the 0.11. However, when x is 10, you get 1 over 10, which is 0.1. So as you come out here to the right, you're getting very small numbers. Likewise, if you go out to the left, you're getting very small numbers. 1 over negative 10 is going to be negative 0.1. But what's happening in close to the x value of 0? When we're in close here toward x equals 0, so let's take a very small positive number. So if we had like x equals 0.001. So that means the y value would be 1 over 0.001. So that's like 1 over 1/1000th, which when you divide by a fraction, you reciprocate and multiply. You reciprocate the denominator, multiply, you're going to get 1,000. So as you get in here close to x equals 0 from the positive side, your y values blow up. And if you put 1/1,000,000th in there, you would get 1 million. So the closer your x values get to 0, the higher your y values go. And of course, the same thing's going to happen on the other side. If we put negative 0.001 in there, it's going to turn out to be negative 1,000. So as you come in toward x equals 0 from the left side, from the negative side, you're going to get large negative numbers. So that's why we get that thing dive bombing down. So good old reciprocal function. Again, I mentioned up here in the note that it's a very special function, that it is its own inverse. And we really don't know exactly what that means yet, but the very next section we do, section 1.4, we're going to talk a lot about inverses. That is kind of a big deal. Okay, back to a really straightforward one, the absolute value function, which we've looked at a little bit before. These guys always give kind of V-shaped graphs, like a giant capital V. And we're going to, not do a ton of work with these guys, but we can take that vertex, this guy down here, just like the vertex of a parabola, and, we can move it so that you get a V graph that looks like that, or maybe one that gets reflected and goes upside down like that. We're going to do a lot of that later on in this chapter as well. Notice the domain and the range are very, very similar to y equals x squared. It's identical to y equals x squared. So you could sort of like a rigid parabola where these things are straight line segments instead of being curved. It's kind of special, so it's kind of important. Now, one thing I want to do with that guy is how could we describe this function, absolute value, without using absolute value bars? In other words, what happens to x? If you think of a function kind of sort of being like a nightclub, x has come in, and then they come out as new numbers, okay? They get turned into some new number. For example, if we had a simple function like, 2x plus 1, x value goes in, and he gets doubled, and then we get 1 added to him. And he comes out as this new function, f of x. He comes out as a new element called f of x. So, if a 1 went in here, he's going to come out as 3. If a 5 goes in there, he's going to come out as 11. So you think about, well, how do we describe absolute value other than say you absolute value it? Because what does absolute value do really to numbers? Well, most of you know exactly what absolute value does to a number. The absolute value of 3, for example, is just 3. It doesn't do anything to some numbers. And if you think about what numbers does it not do anything to, I think you'd agree that certainly positive numbers, the absolute value of the positive number is exactly the same as the number itself. So it's kind of like our very first function, y equals x. When x is a positive number, the absolute value of x is that number. Couldn't be more basic than that. However, what does absolute value do? When does it do something? Well, it does something when it acts on negative values. So what we're going to do is set up what's called a piecewise defined function. This function is defined in 2 pieces, and those 2 pieces are one rule when x is greater than or equal to 0, and another rule for when x is less than 0. So you might want to sort of think about this like like the line at the movies. When you go to movies, you're going to buy a ticket, and they have like different rules for what the prices are depending on how old you are. If you're less than 12, you get to pay the kids' price. So, a person going up to the line says, okay, well, my age is 12, or let's say his age is 10, so he's clearly like less than 12. He's got 2 prices to pay. Well, the rule is if you're less than 12, you pay the kids' price, which is like $9. I don't know what it is. Maybe let's say it's $8. But if you're somebody, so he would go pay $8. But if the person comes in that's like 13, they have to pay the adult price, and that might be something like, I don't know, 11 or 12 bucks. So we have a situation there where the function's kind of defined in 2 pieces. One if you're less than 12, and another one if you're greater than, or I should say greater than or equal to 12, not greater than or equal to 13. So you get an idea of how this could have real-world applications. Well, the function works the same way. When a number comes in, it has to first ask itself, well, am I a number that's bigger than or equal to 0, or am I a number that's less than 0? And just like we said, for numbers that are larger than 0 or 0, the absolute value of x is just whatever that number is. Okay, the absolute value of 7 is 7. The absolute value of 13 is 13. The absolute value of 0 is 0. So anything where the x value going in is greater than or equal to 0, the answer is just going to be whatever that number is. However, for numbers that are less than 0, what we have to do is take the opposite of that number. So for example, when a negative 3 goes in and gets absolute valued, let's say negative 3 goes in, he comes out as 3. What I need you to do, though, is understand that 3 is the opposite of what went in, okay? So any negative numbers that show up, those are going to be exactly the same as whatever it was when we started. Okay, sorry about that. I hit a button here and it started going crazy on me. So just as I was saying, if you put a negative number into this absolute value function, the absolute value function will actually turn that number into its opposite. So the result here, to fill out our piecewise defined function, is if x is a number greater than or equal to 0, that number just remains the same. It's unchanged. But for any negative numbers, the function will take the opposite of that number. So you would write f of x can be defined, the absolute value of x can be defined as x for values of x that are greater than or equal to 0, or the opposite of x for values of x that are less than 0. And so then you've seen your first look at a piecewise defined function. And that's going to be something we're going to look at. In fact, at the end of the homeworks, you're going to see some questions about piecewise defined, and I expect we can talk about them a little bit more tomorrow in class. Okay, we're down to our last few here. the integer function. Notice this funky double bracket thing. Sort of looks like absolute value, double absolute value bars. Not a function we're going to work with mathematically at all, but it's just interesting to realize that such a thing exists. The graph, as you can see over here, kind of looks like this set of steps that somebody might be going up. So it's sometimes, these things are sometimes called step functions. And what's happening with an integer function is it basically just takes any number that you plug it in. So this integer function takes any number that you plug into it and just kind of rounds it down to the next nearest integer. So for example, integer 1.312 would just become the number 1, okay? If you had 17.39 and you integer that, it's just going to become 17. Now you might say, hey, this is rounding. It doesn't matter though. You could put in 1.999, and even though that's really close to 2, the integer function doesn't look at any of this stuff over here. It just says you're now going to just get knocked down to 1. So it's not exactly rounding it according to the rules of rounding that you learned in grade school, but it's just going to knock it down to the previous, the next smallest integer. Now, think about it a little bit. When you go an integer function, negative 2.9, if you have to think about on the number line, here's 0, negative 2's there, negative 3's down here. So if you're thinking about negative 2.9, that's going to be just there on the right side of negative 3. So the integer function isn't going to round negative 2.9 to negative 2. It's going to take it to negative 3, which was the last integer that it passed, sort of. So that's a little bit tricky. That'd be negative 3. Now, what does the graph look like? The only thing you're not really seeing here is what happens at the endpoints of these little steps. So if, as I say up here, the filled in circles would be on the left side. Okay, these things. Because when x is 3, the integer value for 3 is 3. Okay. However, when x is 3.9999999, right there, it's going to knock it down and keep it at 3. So you're going to be stuck right there. However, as soon as you go up to 4, you're going to get, as soon as your x value becomes 4, you're going to become the next integer. So we have closed circles on the left and like open circles on the right sides of these things. So I knew I wasn't going to be able to draw that on the graph, but I thought we could just talk about it here. I'd say the most practical application of that is if I went around the classroom and said, okay, how old are you guys? I don't think anybody would say, I'm 16 years old, 4 months, 3 weeks, 2 days, 11 hours, and 13 minutes, and 26 seconds. You would say, I'm 16. Okay, so you took your age and you just truncated it. Even if your birthday was next week and you were going to be 17 next week, you'd probably still just say you're 16. So you're kind of using the integer function every time you state your name. So that's, it's not a big, like I said, we're probably never going to see this symbol again all year, but you should be aware that it's there, and it can do such things. So here we get to our last 2 functions on our 12 basic functions. They are closely related to one another. It's y equals the sine of x and y equals cosine of x for 11 and 12. These graphs are called sinusoids. Even though y equals cosine of x has a co in front of it, it's still called a sinusoid. And if you compare the 2 graphs, they look very, very similar. That they're both bounded functions. They're both bounded above by 1 and below by negative 1. Remember, if a function's bounded above and below, we'd refer to it as being bounded. They both have a domain of all real numbers. You can plug in any number you want and take its sine or its cosine. And you guys might remember the phrases sine and cosine from your right triangle trig, which you studied in geometry, where, say, if you have an angle here, x, the sine of x, whatever that angle is going to compare the opposite side to the hypotenuse in kind of a ratio and say, okay, well, maybe the opposite side is half as long as the hypotenuse. And that actually happens for the sine of 30 degrees. The sine of 30 happens to be a half, because the opposite side would be half as long as the hypotenuse would be. Now, you might wonder, how can we deal with numbers like positive 137,000 or negative 1 million? How do we take the sine of a negative 130 million degree angle? Well, we'll talk about that when we get to chapter 4, when we study trig in depth. But for now, you just need to know, hey, it can be done. I could explain it to you pretty quickly, but it's, again, a little beyond the scope of what we need to do right now. So just know that these functions are never ending. They just continue to bounce up and down between 1 and -1. In order to get a good picture on your calculator, we'd have to talk a little bit about the window settings and what to expect there. And whether your calculator is going to be measuring these angles in degrees, which you're all familiar with, or radians, which only some of you might be familiar with if you've talked about radians in physics yet. But degrees and radians is kind of like the difference between, say, meters and feet. It's just two different units of measuring angles. But the important thing to take out of these guys is that they are, the domains are all reals, and that they're bounded functions between -1 and 1 inclusive. So there you go. Most of the homework is going to be, there's some matching where you're going to say, okay, find this function and then go find its graph that's given. And then there's another section that says, okay, find me, say, several functions, find me 3 functions that are odd of these 12 basic functions. So outside of that one glitch where I had the exponential function, I had the wrong picture in there, but once you fix that, you should be able to answer all those questions. So that's going to be it. I think on the next, I'm going to make another slide, just make sure I give you guys a good picture of what y equals e to the x looks like. Okay, so this will act as the corrected version of what the graph for y equals e to the x should look like. We'll make a little table of values here and then plot them. So again, when x is 0, we're plugging a 0 in for our numerator. We would have 2 to the 0th power, okay? Or I'm sorry, 2.718 raised up to the 0 power. Well, anything raised to 0 power is 1. So we get our first data point at 0, 1. Next, we'd have 2.718 raised to the first power, which is going to be 2.718. So I come over here to x equals 1 and go up about 2.718, and you can see this thing's growing. Now, at x equals 2, 2.718 squared, I think like I said before, it's going to be somewhere around 7. So by the time you get up to 2, you're going to be way up here at 7. And then from there, you're just going to continue to blow up, and these values are going to go way up there real fast. Exponential functions grow really quickly. They're the fastest increasing functions. Now, as far as what's happening on the left side of the x-axis over here, perhaps I should put some numbers down here to remind you. -1, -2, -3, and -4, for example. So when x is -1, we'd have 1 over 2 to the 2.718 to the first power, which again, like I said on the other page, is about 1/3. So we'll say it's about 0.3. So at -1, we got a y value of 0.3. So this thing comes down like that. And then, I just threw in one more. So 2.718 to the -3rd power is 1 over 2.718 to the 3rd power. And 2.718 to the 3rd power, that's going to be somewhere around 25 or something like that, 20. So let's say this is 1 over 20, approximately, which is about, what, 0.05, right, 5%. So we're talking, by the time we get up to -3, we are really, really low. All right, so that's what the function of y equals e to the x looks like. Domain -infinity to infinity, and your range is 0 to infinity. Put a little positive there. All right, guys, you should be able to handle the homework now. Have a nice night.